Steel, timber, rubber, glass, stone, clay, wool, cotton. From such materials, men have made everything they use. Into this world of traditional materials is born a new material. At the line of contact between these two liquids, long chain molecules are continuously forming into a new material, a polymer of a kind not found in nature. All plastics are made from polymers, but though hundreds of different polymers can be made, most of them, like this one, are useless. The challenge is to make a polymer which can be used. Here is one way of doing it. A powerful catalyst starts a violent chemical reaction in which single molecules or monomers are induced to rearrange themselves into long chains or polymers. These chains are thousands or even millions of monomers long, and making them is the key science of the plastics industry. When the polymerizing reaction is complete, the result is called a plastic. In its first form, it is a fine powder. If the polymer is a good one and the pressure and temperature are right, the grains of powder will flow together. A good polymer may take years to develop, but once you have one, it is worth backing with men and machinery and millions of pounds. This is styrene, 3 tons of it. To make it polymerize into polystyrene needs careful control for about 12 hours. The reaction is successful when the beads of polystyrene can be seen sinking to the bottom of the sample. When the reaction is finished, a stream of polystyrene is run out into the plant. Monomer into polymer, styrene into polystyrene, dried, tumbled, colored, extruded, and cut into thousands of tons of plastic granules. The base material for an industry. Only 3 days' output from this plant produced enough plastic to make 3.5 million beakers. Enough for the Nigerian government to give one to every child in the country. There are dozens of different plastics to choose from, but they all belong to one of 2 groups. The first group is the thermosetting materials. As a thermosetting plastic flows, the long chain molecules are formed and slide over each other. When the reaction stops, the chains cross-link and set permanently. Heating will not move them. The thermosetting principle can be used to make plastics of many kinds: sheets, laminates, paints, and foams. This polyurethane foam is being made by the one-shot method. The chemicals are reacted simultaneously to produce, in a few seconds, the long-chain polymer molecules that build up into a rigid foam. Now for the second group, the thermoplastic materials. To form this sheet, the plastic has already flowed once. With the right temperature and pressure, it can be made to flow again. When a thermoplastic is heated, the long polymer chains flow over each other. As it cools, they set. Heated again, and the chains move again. The plastic will alter its shape once more. This is the fundamental characteristic of thermoplastics: to flow once and flow again. For use in industry, they are first made to flow into granules, a convenient raw material. But before the granules can be shaped into a finished article, they must be heated again. Then the plastic can be forced into a mold of any shape you like. In practice, the shaping and reshaping can be done several times. In this village in northern Greece, the people have got together to put in a new irrigation system, using pipes made of polyvinyl chloride, or PVC. Because the pipe is a thermoplastic, each family can make all the joints for its section simply by heating the pipe ends and shaping them with a former. Like this, people quite untrained can make hundreds of joints a day. Mass production, and thermoplastics are ideal for it. In 1 year, 750,000 tons of polystyrene, 1.5 million tons of PVC, 1 million tons of polyethylene, 120,000 tons of polypropylene. Before the war, there was no organized thermoplastics industry at all. Today, world output is 3.5 million tons. And with this expansion have grown other industries to produce the ingenious molds and machines that make the plastic flow into any shape and any thickness. This PVC powder will flow into a sheet 1/16 of an inch thick for floor covering. One grade of polyethylene will flow onto paper and give it a waterproof coating less than 1/1000th of an inch thick. Another grade of polyethylene granules can be blown into a transparent film making 2.5 miles in an hour for packaging. One grade of polypropylene can be drawn into a filament as strong as steel and as soft as silk. Another grade of polypropylene can be injected into a mold to make 6 combs every 20 seconds. Polystyrene can be injection molded to make a part for a slide projector to a tolerance of a 200th of an inch. A few pounds of polystyrene can be heated and expanded to 50 times its original volume to make a rigid insulating block containing millions of minute air cells. Once the material is chosen, there may be several ways of processing it, and the choice is not easy. By vacuum forming, this polystyrene sheet can be made into a refrigerator liner. Mold is cheap, under £1,000. But polystyrene in sheet form is dearer than granules, and the machine makes only 20 an hour. A different machine uses granules of polystyrene to make a refrigerator lining by injection molding. The raw material is cheaper, and the machine is twice as quick. But the mold costs £10,000. Vacuum forming, injection molding, extruding, blowing, calendaring, casting or coating. Whatever the technique, all thermoplastics have one thing in common. They will flow into any shape, however complicated. But in every other way, they differ significantly, so that today there is a material to meet almost any need. But it has been found that plastics have an enormous variety of physical properties.
Nee, oké. Wil je misschien op de Fischer met de ringmandelcombinatie 1814 de IB13, Kalona IB13 blazen? Nou, ik zal even kijken of het kan.
Some have good tensile strength, others haven't. Some are brittle, others are tough. Some break down in sunlight, some resist it. Some are good at high temperatures, some at low. All are good insulators, and some are superb. In fact, so wide is the range of properties that the art now is to choose the right plastic for the job. Polyethylene was the right plastic for this job, to insulate 2,000 miles of cable now lying on the seabed between Britain and Canada. How you use the plastic depends on your attitude towards it. And there are many different attitudes.
Day, just a moment, madam. I do the selling, and we're not running a Woolworth counter. Look, there's one, there's another one. Can anybody see good value in it? Lady down there. Thank you. Are you paying? And don't forget to pay. Can you tell me something, dear? Can you tell the difference between that leather bag and that plastic bag? Here, go on, look. you can't tell the difference. Thank you very much. That's how in France we have got on bags in England today. The lady said she cannot tell the difference. Plastic is every bit as good.
Every bit as good. No doubt of it. But plastics are more than an imitation. They are a design material in their own right.
Yes, that's not a bad idea.
You get away with a lower pressure.
Well, we have got trouble with this gate, John. We're going to get a bit of trouble with flooding, which is throwing a bad nit mark. And on these veins, I think if we can have a bit more taper, it'll be a lot easier for extraction. And I think there is an error somewhere on the bosses, which Johnny has taken up.
Well, it's actually on these 4 locating bosses which fit in here. They should fit fairly easily, but...
As with timber and steel, so today plastics are part of the engineer's vocabulary. Plastic tailor-made for the job in hand. But to tailor a plastic for any job, the chemist must predict its behavior at the molecular level. This is polypropylene film. At one stage, the film is cooled and crystals are formed. If the crystals are large and irregular, the film will be dense and cloudy. With faster cooling, the crystals become small and regular. The film will be clear and perfect for packaging. Mass production. Inside the mold, the plastic flows into 600 bottles an hour. It looks so easy when it's going well. The machinery, the mold, the man, the material. Which has made the mistake? These are simple machine faults. Material faults are more subtle. For example, if the molecules from which these granules are formed deviate from the specified size or mass, this will affect the properties of the plastic. Refined techniques are used to check this by determining the average molecular weight. For different grades of plastic have their own average molecular weights, which affect the way they will flow. To keep these properties consistent, every batch must be scrutinized and controlled at the chemical plant. But once the product is made in its thousands, the manufacturer must know how it will behave. In heat, in cold, in contact with acids and solvents, in the atmosphere of cities, in the humidity of the tropics, over months, over years. It's easy to test a pipe to destruction under extremes of pressure. But what does that tell us about a pipe that must lie in the ground for 100 years? After 7,600 hours on test, a pinhole burst. Why? What are the safe working limits for each plastic? There's only one way to find out. Test hundreds of pipes under load for tens of thousands of hours. Only then can you begin to predict the behavior of every grade of each kind of plastic and tailor the material to the job. And when the right choice is made, you can produce by the million, day and night, never stopping. In some countries, plastics are arriving for the first time, arriving as a necessity. In a village where the nearest spring is 3 miles up the mountain, pure drinking water is a luxury. These pipes will bring that luxury to everyone. For some countries, plastics are stimulating new industries to make by the million the essentials for better health and easier living. Traditionally, men have always had to use the raw materials of nature as they found them, in the forests and quarries of the earth. Here is the quarry of the future. The chemical plant, breaking down oil or coal into simple chemical substances, recombining them into a new world of color, lightness, new textures, new forms, new ideas. Plastics are forcing us to rethink how we make things and what we make them of. Like this rope, made of polypropylene, lighter than water and strong as steel. Plastics combine with traditional materials to suggest new solutions to problems of design and construction. Glass fiber and polyester resin will combine to make in only 10 weeks a boat 100 feet long. Plastics now are part of our lives. Seen or unseen, they are becoming more and more important. Some plastics are already well tried and proven. Others have yet to be discovered. For we are still at the very beginning. Carbon, hydrogen, nitrogen, oxygen, chlorine, sulfur, assembled and reassembled into giant molecules of endless variety. An infinity of new materials coming into our reach, not to simulate the world we already know, but to suggest new patterns and shapes for tomorrow, and by their sheer versatility, challenge the imagination of men.